The first message I saw was not a pager alert. It was Slack. Anyone else unable to log in? Then another one. Customers reporting auth failures. I opened the dashboard immediately. API success rate was at 99.98%. Latency was steady. CPU and memory across the cluster were flat. No spikes, no restarts, no crash loops. Everything was green. And yet, the support channel was filling up with screenshots of login screens that just kept spinning. No error message, no 500s, just stuck. Our synthetic monitoring checks were passing. Health endpoints were returning 200. Load balancers were healthy. Pods were healthy. But real users could not authenticate. That disconnect is what made it dangerous. We were running in AWS primarily in US East 1 with a secondary region in US West 2 for disaster recovery. Production was a Kubernetes cluster on EKS, about 40 nodes, spread across 3 availability zones. Traffic averaged around 1,800 requests per second during peak hours. Login traffic was about 15% of that. Authentication was handled by a dedicated auth service deployed as a separate Kubernetes deployment. It validated credentials and issued JWT tokens. It depended on RDS for user records and Redis for session metadata. We used GitHub Actions for CI and Argo CD for GitOps-based deployments. All services were containerized, and deployments were progressive rollouts with readiness and liveness probes configured. Monitoring was Prometheus and Grafana for metrics, Loki for logs, and CloudWatch for RDS metrics. We had alerts on error rates above 2% and latency above SLO thresholds. On paper, it was a mature setup. That morning, none of the alerts were firing. From the user perspective, login requests would hang for about 20 seconds and then eventually return a generic timeout error from the front end. From the back-end perspective, the auth service was not returning 500s. It was not crashing. Its HTTP success rate metric looked normal. That was the first misleading signal. Our metrics showed a steady request rate. The auth pods were responding to health checks. CPU usage was modest. Memory stable. Database CPU was low. RDS connections and Redis memory were fine. What looked suspicious was one subtle metric. The 95th percentile latency on the auth service had crept from 120 milliseconds to about 2 seconds, still below our alert threshold of 3 seconds. And because the front end had a 20-second timeout, those slow responses eventually became visible to users. But the success rate counted them as successful. From our perspective, the system was healthy. From the customer, it was broken. My first hypothesis was database contention. Logins hit the user table and sometimes update timestamps. I checked RDS metrics. CPU low, disk IOPS normal, no read replica lag, connection steady. I checked auth service logs in Loki. No obvious stack traces, no spikes in error logs, just slower response times. I started sampling individual request traces. That is where it got interesting. Each login request spent about 1.8 seconds waiting on a call to Redis. Redis latency metrics were not alarming. Average command latency was fine, but the trace showed repeated retries around session key validation. We dug into Redis logs. No failures, no evictions. At this point, someone mentioned that a new rate-limiting feature had been deployed the previous evening. It introduced a Lua script executed on Redis. We pulled up the Argo CD dashboard. The rollout had completed successfully. No failed pods, no restarts. Maybe the Lua script was slow under certain patterns. We simulated login traffic from a staging pod. The script executed fast in isolation. Then one of our SREs asked a good question. What is the Redis connection pool size in the auth service? We checked the deployment configuration. The connection pool was set to 50 per pod. We had 8 replicas. That meant up to 400 concurrent connections. Redis was configured with a max client limit of 500. Normally that was fine. But we checked the CloudWatch metric for connected clients. It was hovering at 498. We had almost exhausted the client connection limit. There were hundreds of connections in idle state. Then it clicked. The new feature had introduced a subtle bug. It created a new Redis client per request in one code path and did not reuse the pooled client. Under peak login bursts, it leaked connections until we hit the Redis max client limit. When Redis hits the max client limit, new connection attempts block until a slot frees up. That blocking was not throwing errors, it was just stalling. That explained the latency and why health checks were fine. But we still needed confirmation. We scaled the auth deployment from 8 replicas down to 4 temporarily. That reduced the total connection footprint. Within minutes, connected clients dropped to around 300. We had our culprit. The root cause was a connection leak. Specifically, a conditional branch that handled password reset attempts instantiated a new Redis client instead of using the shared pool. It did not close it properly. During the spike, it exhausted the limit. No error was thrown, just delayed execution. We had two options, rollback or hot patch. We opted for a forward fix. One engineer prepared a patch to reuse the shared pool. We deployed via Argo CD and temporarily increased Redis Max clients to 1,000 for breathing room. After deployment, connected clients stabilized around 320. Auth service P95 latency dropped back to 130 milliseconds. Front-end login success normalized. Total user visible impact lasted about 47 minutes. What failed was not Redis or AWS. It was a subtle resource leak combined with a monitoring blind spot. Our detection was weak because we did not alert on saturation or tail latency. We assumed success rate meant acceptable user experience. It was not. Architecturally, we had a single Redis instance for critical paths, increasing blast radius. Organizationally, the feature did not go through load testing at realistic peak concurrency. We tested functionality, not resource behavior under scale. First, monitor saturation metrics. Second, tail latency matters more than averages. Third, shared infrastructure needs strict connection management. Fourth, progressive rollouts should include resource behavior validation. Finally, success rate should reflect user-perceived success. Green dashboards do not always mean healthy systems.